Okay, welcome back everybody to another week of numerical algebraic geometry. This week we'll move on to parameter homotopes. So let me remind you of the story so far. The story so far has been we want to solve a univariate polynomial system, meaning we want to find approximations for all the complex roots of that polynomial. So what we do is we cook up a system that looks like it via this Bezier system or total degree system. It's just x to the d minus 1, where d is the degree of the polynomial we want to solve. And we set up a homotopy which deforms the solutions to that total degree system to the solutions of the system that we want to solve in the first place. And we've seen the picture I keep drawing where the x-axis is the t-axis, and then we have the solution space, which is C, and these paths go through the board. And I keep drawing that over and over again. And then in multivariate homotopy continuation, we extended that vertical axis to go from C to the n. We were solving multivariate polynomial systems. We kept things square, but we were solving multivariate polynomial systems. So the solution space became C to the n, and our solution paths traveled through C to the n as t went from 1 to 0. So t is still hanging out in this interval, this real interval from 0 to 1. Although occasionally we have stepped out of that via the gamma trick to make a new path through the complex space C with coordinates t. So that was useful. So that was the one time that we extended our parameter space from just this unit interval to actually a complex space. Okay. And extending that parameter space gave us a better view of what was really going on. And it allowed us to avoid these singular t values where paths cross. Now, in this chapter, we will extend the parameter space further to some c to the k. So we will no longer just have some parameter t, we will have many parameters. The nice thing about this is that we're going to see a setting where we can parameterize many polynomial systems which look the same. And so as we move through, we don't have to worry so much about solutions going off to infinity and things like this. So I'll show some examples. So that's the story. But I'd like to start using some language, and I'd like to start being a little bit more precise about it. So as we discussed in the beginning of the course, we're going to need some aspects of algebraic geometry along the way, some definitions, some theorems, and we will pull those in as necessary as we go along. I think a lot of what I'll talk about today is already intuitively ingrained in you, thanks to your mathematical background. So things like dimension, components of a variety, things like this. But let's get some actual definitions that we count on, just in case. Okay. Any questions? Okay. Definitely. Variety x, yeah, it's irreducible if not be written as y and z are varieties neither containing the other. If you're not irreducible, you're called reducible. So for example, if I asked you to prove that a variety was reducible, what would you have to do? What tasks would you have to accomplish according to this definition? Yeah, so I would try to write my variety as this y union z. And then further, I would have to make, so I would have to prove this equality. So any point at x is either in y or it's in z. Any point in y or z is in x. Then after I prove this equality, I would then have to show that y is not contained in z, and z is not contained in y. And I would have to show y and z were varieties. So how do I show something's a variety? I would have to, yeah, exactly. I would have to find polynomial equations which cut out y, polynomial equations which would cut out z. Right? So those would be the tasks I would have to go through to prove something like that. Let's take, for example, so this is a reducible variety. I have written the union, equations for the union, the equations for this point, x and y minus 1, and this parameter. Good. Whereas x this is reducible. The variety, this is irreducible. This is Alex's, I think, right? So that will be called Alex's example for the whole class. You kind of want to write it as the union of the parabola and this point, but this point always already lives on the parabola. Albeit something funky is going on the algebra side. The dimension of an irreducible variety is the largest length of a chain of irreducible subvarieties. But no cheating. You can't just copy a bunch of the same thing, because then this number wouldn't exist. That's kind of a funny definition of dimension. It doesn't really track maybe the dimensions we've seen before. This is the notion of the topological dimension. It's the easiest one to give without handling all these caveats. And I don't want to lie to you today. Great. So, for example, the dimension of the parabola is 1, because I can pick a point inside the parabola, and that's as big as I can get. proving this is a little trickier. You would have to actually prove that there's no way I can find a variety containing a point on the parabola and properly contained in the parabola. One can think about the difficulties involved in proving that. But for now, I just want to give a good definition. So for example, the sphere also. Dimension 2. If I could find a circle hanging out in the sphere and a point on that circle. And so x0, x1, x2 in the dimensions 2. Our varieties all come embedded in some ambient space, c to the n. That's how they're cooked up. You have to be the zero set of a polynomial and n variables. So all of these varieties live in an n-dimensional complex vector space. The codimension, sometimes I'll call it the complementary dimension of a variety, of an irreducible variety, is n minus m. So the codimension of a sphere in 3 space is 1. The codimension of a circle in 3-dimensional space is 2. The codimension of a point in 2-dimensional space is 2. The dimension of a point is 0. And the dimension of 2 points has not been defined yet, because we only have dimension for irreducible varieties. We do not have a dimension for this union of varieties yet. Here. Every variety can be written as the union of a bunch of irreducible varieties in essentially a unique way, and coordinate in a finite way.
I think up to permutation is redundant
Why?
because when you say finite union, that already takes care of permutations, right?
Well, let's call this point y, and this parabola z. X can be written as y union z, which is a different union, although it's the same set as z union y. So I'm saying the way you write it is unique up to permutation. So you could put the xm there, and that would be a different way of writing it, although it is unique up to permutation. Ignoring permutation, ignoring which variety you put in first, second, third, fourth, fifth, it's the same. And these xi are called the irreducible components of x. This one's a fun one to prove. Just give you a sketch. All right, x is either irreducible or it's not. If it's not, you can write it as a union. And you can keep on applying that question to each one of the constituents of the union. And you have to argue that it stops eventually. And this is by no theory and any of the polynomial ring. So you don't even need prime ideals or anything like that here. This is called an irreducible decomposition. Uh, So a point on a subvariety of C to the n of dimension m is called smooth if there locally exists a parameterization of x near e So this is the technical definition I didn't want to give, right? But it avoids Alex's problem. Okay. So a point is smooth on a variety if there locally exists a parameterization via a holomorphic map from an m-dimensional complex space of x near P, which we're just going to say is the image of 0 here, such that the Jacobian evaluator at P has full rank. Okay. So why does this solve things? Because it only cares about the geometry. It doesn't care about how you represented x, right? So Alex's representation of the parabola in this x times the equation of the parabola, comma y times the equation of the parabola, which we kind of draw like this, but as a set, it's just the parabola, and I can still parameterize this point locally via holomorphic map, specifically he goes to t comma t squared. This might be. And indeed, this has full rank at t equals 0. Jacobian t 0. It's rank 1. It says big of a rank such a matrix can have, thanks to the rank null. So that's what I mean by full rank, as big as possible for the size of the matrix. Otherwise, P is singular. Good. Most people you have a definition in your back pocket. You need one. Not because I feel better about what I said last week now. Any questions? Now I want to make rigorous what I mean when I say the word generic. Property P of points on some irreducible variety X is said to hold generically if there exists a proper subvariety, where if you avoid that subvariety, that property holds. Examples. Here's an irreducible variety in the plane. And I might say the kind of sentence like, generically, it's non-singular. So how would I prove this? The first thing I would have to do is I would have to prove that the set of points which are singular form an algebraic variety. So, one, singular points X is a subvariety of X. So I do this by writing equations down. The next thing I would have to do is just exhibit some point which is not in that variety, because that would mean it's proper. Is anybody interested in why we can write down equations for the singular locus of a variety? Yeah.
I think those would be cut out by minors of Jacobian. I don't know, just a guess.
Yeah. Okay, so there was this thing that I told you which was true in spirit last week, which is that there are equations for the singular locus. It's when the Jacobian matrix drops rank. Now, because we all remember everything that's ever been said to us about linear algebra, we definitely all know that a matrix has rank less than m if and only if all the minors of size m and bigger are 0. Well, those are polynomial equations. Okay, so being a matrix of some rank, of at most some rank, is an algebraic variety. You can write down the equations, which is the minors that need to manage. The easiest example is an n by n matrix has rank at most n minus one if the determinant vanishes. Right? Okay, so we all remember that. And so if you believe what I said in Spirit last week, then you believe that as soon as I write down equations for x, I can write down the Jacobian as a matrix of polynomials. I can take all those minors, and that's the singular locus, that along with the equations cutting out x. But then there's Alex's example, which just throws a wrench into the whole thing. And so the thing you need to say is that this Jacobian thing I said last week, and this is only for people in the know right now, okay? So don't worry if you don't know what any of this means, it's okay. The irreducible varieties and the numerical irreducible decomposition correspond to prime ideals. If you do what I said last week on the equations defining a prime ideal, what I said is correct. It really does just depend on the ideal. It doesn't depend on the generators of the ideal. That's an exercise. It's kind of fun. But yeah. Okay. And so if I wanted to write down equations here, I would find a prime ideal, generators for the prime ideal of polynomials which vanish on x. I would write down those equations, I would write down the Jacobian, I would take the minors. That's a whole bucket of equations, super overdetermined. Gives me a variety contained in here. And then I just need to find one point where it doesn't hold.
No point.
Yeah, so one point, which is exactly. So one point with these equations defining what it means to be singular does not hold. That's right. So why is generic so great? Because generic for us, for the purposes of this course, works really well with like choosing random numbers. So what do I mean by this?
It doesn't have any condition on the dimension of subvariety or anything. Any proper subvariety would do.
Yeah, I mean, it's got to have dimension at least one smaller than the big variety. By definition of dimension, that's actually a really nice, easy thing to prove with our definition of dimension. Right? Because as soon as you go down one irreducible variety, your chain has to be one smaller.
The prime ideal drops by one.
Okay. Yeah, it's the Kroll for the prime ideal. Okay, so anyway, yeah, for example, like I could say that generically on this variety, none of the points are this point. Okay. So that's kind of something silly. Okay. Proper subvarieties are much smaller than the variety they live in. Irreducible varieties. Okay. Think about this for a second. So like, if I'm inside C, and I'm a proper subvariety, what am I? I'm a finite set of points. By more. And a finite set of points is way, 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 way smaller than all complex numbers. So much smaller that our definition actually calls the dimensions lower. Right? Dimension is dropping when you look at proper subvarieties of irreducible varieties. Yeah, it's important that the top thing is irreducible. That's why I went through all this. For example, here's the union of two circles, called x1 and x2. And x1 is a subvariety of the union, but it's not much smaller than the union. It's half of it, right? So this is not what I'm talking about. I'm talking about an irreducible variety and then some subvariety, proper subvariety, for example. And the subvariety doesn't have to be irreducible. you like measures, any continuous measure on irreducible X as measure 0 on a proper subvariety. Any continuous measure. In particular, any probability measure. So if I have any probability measure on the circle, for example, I can say with probability 0, I will hit any of these points. And with probability 1, I will miss all of these points. Equivalently, generically, I'm not any of these points. And this is how you would make rigorous questions like how likely is it that X happens, which I think is the terminology we use on the first homework assignment. I asked you how likely is it in univariate homotopy continuation for the point X star P star to be actually a singular point on the union of solution curves. Okay, so we're not going to get to parameter homotopies today, but we're going to get all the nitty-gritty out of the way so we can have a lot of fun on Thursday. In my opinion, this is the chapter where things get fun. Okay, so things that are generic. Okay, so this, for example, say things like a generic quadratic equation in one variable has two distinct complex solutions. And we're going to say sentences like this a lot. And it's important for you to be able to connect that to what's going on over here. Okay, so I want you to think for a moment, what is the irreducible variety here? And what is the subvariety here? Indeed, if I randomly pick A, B, and C, I'm going to have two distinct solutions. Really connected to this definition.
So I think your variety would be C parameter space, and the subvariety would be B square minus 4AC.
Almost. Say again.
It has to be.
Yeah.
Non-zero.
Right. So avoid that.
Mhm.
B squared minus 4AC cannot be 0 because then you get a solution of multiplicity and you don't have this property. And A has to be non-zero, so you don't lose 1 point off to infinity. Right? Good. What else do I have? There you go. Okay, let's do 8 minutes of spoilers for parameter homotopies, just to anchor concepts for Thursday. We'll re-say everything on Thursday. And then we'll take 5 minutes for questions and then we'll be done with this. So before we have this t-axis, and we solved things up here. So this was our solution space. And we may or may not have loosely discussed t as a parameter. And then we have these curves. Here. And where did these live? Well, upstairs, we're not just tracking the solutions, we're also tracking the t-values for which they are solutions. So we have this x living inside cx to the n plus t. And we had a map down to the parameter space, which was kind of a silly map to consider, but it was d to 1 generically, which means for all but a subvariety of the parameter space, the fiber of this map is exactly d distinct solutions. Okay, this map is generically d to 1. We know exactly what that means now. We are not tasked with the responsibility of identifying that subvariety. Rather, we just need to identify that it is a subvariety. Okay. All right, but it's generically d to 1 for some d, and that's the number of solutions paths. And we're going to soup this up so that we consider, so the story now will be this. We'll have a solution space, just like before. We'll have a parameter space, so we get more parameters than just t now. So this picture becomes a little bit bigger. Instead of have solution paths, we might have like a whole solution surface. We still have the projection that's going to forget about the solutions. Just give me parameters. And the fiber of that projection will still be d points generic. And now if we want to move from one fiber to another, well, then you can just parameterize this by some unit interval, write down the corresponding equation, homotopy, and then solve it using multivariate homotopy. So you can always restrict paths in here in the parameter space to just these real one-dimensional paths and move around. Because we already know how to do multivariate homotopy integration. So we're going to be able to move around this picture using the technology we've already developed. Although this picture is going to be much, much more illuminating. It's going to tell us what's really going on. For example, sorry, and crucially, this variety x up here will be cut out by a parameter that's called nonce. So, for example, x squared plus bx plus c equals c. This gives me something I'm going to try to draw the real picture. In three-dimensional space because it lives in Cx, Cc. And I can project this down, 2-to-1 map, onto the BC plane. Okay. And we know that there's this discriminant or exceptional set, b squared minus 4c. And what are these points? These are points where if I drew the vertical line, that would actually be tangent to this surface here. And you can think, if I come off here, I'll have like 2 points. I go under the Pringle, I go above the Pringle. And then if I were to move here, those 2 points would come here. just like it does in solution paths. But this is much nicer to look at, because now instead of just thinking about this one-dimensional picture with the total degree homotopy, we can think, okay, well, what is the Brysiewicz start system? What are the BC values? It's just 0 and -1. So this point here corresponds to our Brysiewicz start system. We have x equals -1 and x equals 1 up here. And that's an easy fiber to solve for. And then what are we doing when we do a homotopy? We're just doing a straight line path to wherever we want. We're doing that over and over again. And one of the mistakes people made in homework, which I only took off a itty bit about, was that you used a real start system to try to solve for like 10,000 quadratic equation solutions. And so some of those went through here, and you had a path cross. Because you didn't do any gamma trick, you just did straight line, and you can see that picture. Whereas if you use complex start system, you wouldn't have that issue, but we'll deal with that later. So that's the story, and this is a much, much better picture to have in your head when you're thinking about solving a quadratic equation. You see exactly what's happening with the paths. It's all packaged into one gadget, which is a dominant map of irreducible varieties of the same dimension. And that's all I'll say. And then next Thursday, we'll unpack what that last is. Okay. So I'll stop the recording. I'll take questions, and then I'll let you go.